Green.
Great, you're all set. Go ahead.
Okay. Hi everyone, I'm Linli Jia from WSU. So today the topic of my presentation is coordinating energy resources in an islanded microgrid for economic and resilient operation. Today my presentation would going on in these outlines. First, I'll introduce the background of developing this work, and then will be the first main part of our work is the economic operation modes and the proposed resiliency operation modes. And third is resilience metrics used in this work to qualify the improvement of the proposed resilience operation modes compared with the Euro economic operation modes. And lastly would be the test cases used in our work for validation. So the incentive of this work is like this. As we all know, in normal operations, economy and reliability is the main concerns for resource coordination. But for some extreme events like earthquakes, hurricanes, avalanches, in these scenarios, economy would not be the main concern, and the operation focus would move to resilience, like how to supply more critical loads during these events, and how to avoid power loss. So the normal resource coordination strategy may not be suitable for this kind of extreme events. Another incentive is as increasing number of DERs are included in distribution power system, this enables the power grid to form several microgrids when affected by these extreme events, and which enables part or even whole critical loads keep supplied by the DERs. So a proper resource coordination could increase power system resilience and supply more critical loads for longer time, even when affected by these extreme events. Another more realistic incentive for our work is inspired by the operation need of a real-world islanded microgrid. Those power supply resources consist of small hydropower, diesel, battery, and battery energy storage system. In conclusion, the main contributions of our work including two aspects. First, we develop a resilience-based resilience coordination strategy for the islanded hydro diesel battery microgrid. And secondly, we include the resilience metrics we developed from previous work in our this paper to codify the improvement of the proposed resilience coordination strategy against the extreme events compared with the Euro economic operation strategy. So here's the introduction for the Euro economic coordination strategy and the resilience coordination strategy proposed in our work. So usually, since economy is the main concerns of operation, so largely it depends on the generation cost of different energy resources. For the islanded microgrid considered in this paper, whose resources consist of hydro, diesel, and battery, obviously, small hydropower is the cheapest one, which largely depends on the season. So it's favorable to make the most of small hydropower. And in comparison, diesel is the most expensive one. So and it's limited by the minimum output constraint. So it's ideal to minimum the output from diesel generators. But for the resilience control mode proposed in our paper, like some extreme events are predicted, we are not following the usual economic mode. We expected the storage to fully charged before event comes. So the event detection signal is included in the strategy. We assume event is detected like edge hours in front of the event happens. Before that, the event alert is signaled as 0. When it comes, it's 1. So after including the event alert signal, the operation scenarios of this microgrid can be concluded in 4 scenarios. One is when there's enough hydropower to supply all of the load and reserve capacity demand, and the battery is operated in between discharge. It's meet the discharging requirement, which means in the middle of minimum and maximum requirements, and there's no event alert. So only hydropower is enough to supply all of the load demand. And another scenario is like small hydropower is not enough, but the extra load demand is lower than the minimum requirement for diesel generator. Then battery would participate in the operation. Of course, in this scenario, the battery doesn't have charging requirement. And the third scenario is when the load demand is greater than the power could supply from small hydropower and battery system. And in this condition, the diesel generators would have to participate in the operation. And the last one is like no matter what the status of battery system, when event alert is detected, then we will move to resilience control mode. So here is the flow chart of economic control mode and the proposed resilience mode. We can say from here, the resilience mode is triggered by the event detection. So when an event is detected, it switched to resilience mode before the event happens. For both of them, of course, the network topology and correspondingly the parameters of the network, like the output of different generation resources and status of charge and voltage of nodes, and all of those informations need to participate in calculation first, and then status of the battery would be checked for both of the modes. The difference is for the economic mode, the status of battery is only controlled by itself, but for resilience mode, it is also triggered by the event alert And when there's an event is fully charged and then hold until the event happens, and when there's not enough generation from other resources to supply the critical load, and then the battery system would participate in power supply. So this is basically that's still the idea of energy switch. And the improvement of the resilience mode is lastly checked by the resilience matrix. And after that, the parameters in the network is updated and back to the beginning. So here's the description of the mathematical model for the resilience mode. The objective still be to minimize the total cost of the generation. So the first two items are the generation cost of small hydropower and diesel generator, and the third item is the cost of battery system. Here we can say the status of battery system is included, which is the ID, is charging or discharging. And for the constraints, we include the power balance, which is the equation 7, and 8 and 9 are the power flow constraints. Here we use the sensitive method instead of the linearized power flow to simplify the calculation so that it can be used in real-time calculation more efficiently. And for equation 10 and 11 are the constraints for the power output of hydropower and diesel generators. And for 12 is a model for capacitors for adjusting the voltage. And then for 14 and 15 are the power limits of battery discharging and charging, and 16 status of charging limits for battery, and 17 is how the status of battery is updated as the simulation intervals going on. Well, here we comes to the resilience matrix used in this work for quantify the improvements of the proposed resilience distribution control mode, resilience control mode compared with the economic control mode. So here we consider the multiple variables for the resilience matrix. First, we considered the geographical metric, which means we analyze the resilience of the network from the aspect of a graph. And here we include 4 factors for the geographic metric. So this has been more detailed introduced in our paper. So here I'll skip this part. And for the event impact metric, this is a value manually defined by operators according to the location, and the scenarios can happen at that place. Like if the location is far away from the storm center, then the influence of storm to this place would be lower. So this metric defined by operators would also be lower. And the critical load demand metric is the total critical load demand capacity not affected by the events. And critical load not lost is the proportion of critical load remain in operation when event happens. And total generation means the total generation capacity still available for power supply when some event happens. And this +1 and -1 indicates the negative or positive influence of these factors to the final synthesized resilience score. And the synthesis of those factors can be deemed as a decision-making process. So here we include AHP method to synthesize to produce a weight vector for those factors and eventually synthesize those factors into one resilience score. And since those factors are scaled in different units, it needs to be normalized before synthesize. So here's how we normalize those factors according to their negative or positive influence to the final resilience score. Here we had 2 test cases for the method proposed before. First, we use the revised 14 nodes test case, and here's the production cost for different resources. So we can say the problem is formed into a quadratic programming problem, and here we can say the cost of battery is actually not the real cost. So we assume the cost of battery only to signify the preferable of battery generation, which should be between hydro and diesel. And here's the load profile and hydro, diesel, and battery parameters we used in our test case. And from the result, we can say the power from small hydropower is makes the most use for both economic and resilience mode, and the battery system keep discharging and supply power after event alert is detected, which is hour 4. But when the event really comes, here we assumed at hour 9, the battery system has achieved to the minimum limit. So there's no ability of battery system to supply power after the extreme events comes. But for the resilience mode, when the event alert comes, the power is held and the battery system is fully charged and hold until event comes. So it can start to supply the load when event comes and other energy resources are influenced by the event. For the other graphs are the corresponding generation from other resources. The second test case we use is a real-world hydro-diesel battery microgrid, which consists of 2 hydro generators, 1 diesel, and 5 feeders. We assume because of the event, the diesel generator lost the power, and the second feeder also also be disconnected from the network. So besides the output of different resources, we calculate resilience scores for this test case. We can say the resilience score for the economic node is lower than the resilience mode. Our work has been published in IES conference in last year. So if you have more interested in the information, you can check this paper. Okay, that's all of my presentation. I'd like to take any question. Thank you.
Thank you, Lin-Li. So do we have any questions for Lin-Li? You can either unmute or put them in the chat. All right, so Lin-Li, as you talked about this, you on the 14, you've done the original work on the 14 node case. How do you think as you expand to a larger system that this application will work?
Yes, we originally tested the validate the method in 14 nodes, and later the another test case is 55 nodes system, a little bit larger than the 14 nodes, so it also works. But for even larger system, I think it should also be work. We'll test it in future work because for the like the optimization problem, there's no obvious factor to delay the calculation or complicate the process. It should be worked, so we'll test it in future.
So this 55 node islanded microgrid, that's a real test system that you've done the test on, correct?
Yeah, this the structure of this network is come from utility. So it's operated in the islanded mode. Originally, our work is inspired by the operation need of this real islanded microgrid.
So does this microgrid, is there the capability to be connected, or is it the islanded mode, or is it actually islanded all the time?
It's geographically islanded, so it can. There's no transmission line to connect it with mass power grid.
Okay.
Thank you so much for your questions.
Yeah. Are there any other questions? Oop, it looks like someone has a hand up. Suho, you go ahead.
Hello, I could see that you have modeled the battery cost as a simple quadratic equation. So what is the, I just want to know that what is the reason behind that, because we know that there's DOD effect and all those effect, battery cost is mostly highly nonlinear. So how you have modeled it as a quadratic?
Well, yes, according to the literature we referred, there's no actual cost for battery output. So here we define the cost of battery only because the preference of the priority of generation of these resources we define, because here we wanted to make the most use of hydropower, and since the diesel power is most expensive, so we only needed to define the cost of battery among the hydro and diesel. So and then we'll get the generation priority for these resources after solving the mathematical model. So we actually didn't use the real generation cost for the battery. Does this answer your question?
Yes, have you considered this coefficients on your own, and or you have any standard reference?
We get the cost for hydro and diesel from some references, and also there are some literature deal the cost of battery in the similar way to define the cost of battery according to their need. But this equation is designed for because of our need, not come from any reference.
Okay, thank you.
Yeah,
Thank you.
Yeah, just to like
Thank you. We're
clarify.
gonna. Yeah, go ahead,
Yeah,
Sanjeev, real quick, because we're gonna switch to the next talk.
Oh, okay, sorry. So I won't take much time. So why did not we consider like DOD and other things over a period? Because it's considered for only like a few instances of time, or I can say few days. It doesn't consider over years of study. If we take the years into account, definitely we have to take all those nonlinearities from the battery side into the cost. So, but other thing is like we fine tune this quadratic equation to just to make it suitable with the requirement. We do not have any standard way of representing it, but we are somehow we adjust the parameters to make it suitable. Yeah, thank you.
Thank you,
Sanjeev.
Great, thanks, Lin-Li. If you want to put your contact information in the chat for people if they have further questions, that would be great.
Okay, thank you, Professor.
Great. So our last talk